In this lesson, we're going to cover chapter 4.5, which is all about calculations involving Ka and Kb. And we're just going to do the first part of this section. We're going to focus solely on Ka today, Ka calculations. So we're going to calculate concentrations of hydronium, initial concentrations of a weak acid, or calculate Ka, given other things in the question. Finally, we're going to be making some assumptions today in our calculations to avoid things like quadratic equations. So we're going to be stating and discussing some of the assumptions that we'll make in these calculations. So first off, we're going to go back to equilibrium for a second. We talked about solubility equilibrium in the last unit. And in this unit, we're looking at equilibrium with weak acids. The reason why we have an equilibrium with a weak acid is because they don't dissociate or don't ionize 100%. So we have this equilibrium between the full HA, where it's actually together, and then the ionized form, where we get a hydronium ion and the conjugate base of that acid. So we have that in equilibrium. Now, just like all of our other equilibrium equations, we can write an equilibrium equation for this weak acid by taking the products over the reactants. And we leave out the liquid because the liquid cannot change concentrations. So for this weak acid equilibrium, we get our Ka is hydronium times the conjugate base over the concentration of that weak acid. So that leads us to some questions, and this goes back to our ice tables, where we have an initial, a change in concentration, and then a final concentration at the end. We're going to look at some problems and do some sample problems today. So calculating the concentration of hydronium, if we know the Ka, and we might find that from the chart that we were given, that Bronsted-Lowry acid base chart has all the Ka values, and an initial concentration of acid. So here's an example of a question. It says calculate the pH of a 0.5 molar solution of hydrofluoric acid. Now this question will be really simple to do if it was hydrochloric acid that we were looking at, because finding out the pH of hydrochloric acid, we would know that the concentration of hydronium would be equal to 0.5 moles per liter. However, because it's hydrofluoric acid, we have a weak acid that we're looking at, so it will not ionize 100%. So what we're going to do with this question is start by writing down that equilibrium equation. So we've got hydrofluoric acid plus water. Water is acting as a base here, receiving that hydrogen ion. And on the other side, we have hydronium and the fluoride ion. So next, we're going to write down our ice table. And you'll notice I've actually made an IC table because we're going to be working with X as a change. And I've blanked out the whole column under the water because water doesn't change concentration, so we can just completely ignore it from our calculations. So the parts that I know already from my original question is that I have an original concentration of 0.5 molar hydrofluoric acid, and I can assume that I have 0 of the hydronium and the fluoride ion. And this is one of the assumptions that we're making, is that we have 0 hydronium to begin with, because we know that that's actually not quite true, but it's very small compared to the 0.5 molar hydrofluoric acid. Next thing that we're going to do is calculate our changes. We know that because we're starting with 0 on the ion side of the equation, we know that those both have to go up. So we're going to put plus x's on those sides, and they're in a 1-to-1 ratio. And on the other side, those have to come from somewhere, so it's going to be minus x. So at equilibrium, I have 0.5 minus x, and then on the other side of the equation, I have x and x. Now we're going to go back to that Ka expression. So for this one, I'm taking my products over my reactants, and there's my Ka is equal to. Now we're going to substitute in the values for that ice table. So I've got 3.5 times 10 to the negative 4. This one I got straight off of the Bronsted-Lowry acid base table, the relative strength table. And my products, I have x times x, and the reactants 0.5 minus x. Here's where our second assumption is going to come in. We are going to assume that this value is equal to 0.5. We're going to assume that that x is so small, the change in that concentration is so small, that it's not going to affect our significant digits. So we're going to make that assumption. And the reason we're doing that is to avoid a quadratic equation. So I've simplified 3.5 times 10 to the negative 4, that's the Ka value for hydrofluoric acid, is equal to x squared over 0.5, and now I'm going to solve for x. Once I solve for x, what I've done is I've multiplied 0.5 times 3.5 times 10 to the negative 4, and then I've square rooted the whole equation. And I get a value of x is equal to 0.013229 moles per liter. Now I'm still not done with this question because we haven't calculated a pH yet. And so what I'm going to do is I'm going to substitute that x into the rest of the IC table. So here we go. IC table, substituted that all in, and you'll notice that at equilibrium, I have 0.01 moles per liter of hydronium ion. Now this is the one that I'm solving for because that's what is going to be closest to my pH. So if we remember back to 4.4, we can transition between hydronium and pH by taking the negative log of that number. So the last step that I'm going to do in the equation is take the negative log of 0.01, and I'm actually going to keep as many sig figs as I can in there. So I'm not actually putting that into my calculator. I'm putting negative log of 0.013229 in my calculator. And after I do all that, I get a value of 1.9, and there's my final answer. So there were three assumptions that we made in this particular reaction. Number one, we don't include the initial concentration of water. We're not including water. We're assuming that it stays the same concentration the whole time. The second assumption that we're making is that the original concentration of hydronium is 0 moles per liter. Again, that's an assumption that we're making, which is probably not true, but the value is so much lower than what we have with the acid that we're adding in that it's really negligible. The third assumption that we're making is that we're assuming that that 0.5 minus x is approximately equal to 0.5. So whatever that x value is, we're just assuming that it's not going to have any effect on that initial concentration of the acid because that change is so small. One thing to note is that anytime you make that assumption when you are doing calculations, you need to explicitly state that in your answer. I'm going to expect you to do that, and if you go on to university courses, they will also expect you to state that in your answer, although many university profs will also expect you to do the quadratic as well, just to be complete. Okay. Few more practice problems here, and I'm not going to run through them kind of step by step, but I will show you the long answer versions of it. This one relates to methanoic acid or formic acid. So with this one, I've started by writing out the complete formula. You can see that hydrogen is coming off of that formic acid. Written out the IC table or the ICE table, and I've plugged that into the KEQ. That equilibrium constant I got off the chart, 1.8 times 10 to the negative 4, and we're solving for x again. Once we substitute x back into the chart, and I've gotten a little bit lazy here and I didn't write the other two columns down, but we find that at equilibrium we have a concentration of hydronium of 9.487 times 10 to the negative 3. So finishing that off with a pH instead, I take the negative log of that number and I get a pH of 2.02. Again, just a reminder that when we're doing sig figs with pH values, we start counting after the decimal place. So I'm asked for a pH of a 0.50 molar solution. That was 2 sig figs, so I'm answering to 2.02, again with 2 sig figs. Here's another question, household vinegar with acetic acid. This one takes the time to pause the video, see if you can do this question on your own, and then check your answer after. So with this one, here's the final answer. Okay, we're making an assumption again that we are that my final value of this vinegar, CH3COOH, is equal to 0.850, which was given in the question. I go through all of these steps, I calculate the final concentration of hydronium, and that's what's giving me my pH of 2.41. Third example here, again, pause the video, take the time to figure it out on your own, and then restart the video to get the correct answer. Okay, this one actually, sorry, is a little bit different because we are this time given the Ka and the pH, but we actually have to calculate the initial concentration of the acid. So sorry if I mixed you up with this. Okay. In this particular question, we don't have that initial concentration of the acid, and that's what we're trying to find out. So from the question, you can see that I'm trying to solve for that initial concentration of the benzoic acid. I'm going to assume that I have 0 hydronium and 0 of the conjugate base to begin with, concentrations. And the other piece of information that I'm given is the pH at the equilibrium. So the pH I can't plug into the chart directly, it's only for concentrations. What I need to do is turn that pH into a hydronium concentration. So I do that by taking the anti-log. I'm going to take base 10 to the negative 3.30, which will give me an equilibrium concentration of hydronium of 5.01 times 10 to the negative 4 moles per liter. Now from there, I can calculate what the change in hydronium was. And because everything else is in a one-to-one ratio, they're going to all have the same change. On the right-hand side of the equation, they're both going up. On the left-hand side, it's going down by 5.01 times 10 to the negative 4. So at equilibrium, I'm just going to add up those values. You'll notice that the equilibrium concentration of benzoic acid is C0 minus 5.01 times 10 to the negative 4. And if you're not comfortable using C0, C0 is just kind of like an initial concentration variable. You can use X and that's fine. Use whatever variable you want. I'm going to continue using C0 for everything when I'm solving for an initial concentration, just like we did back in the equilibrium unit. So now I'm going to plug that into my Ka expression. So I'm taking my products over the reactants. I substitute everything I know into that equation. I get that Ka from the chart, I think. This one might have been in the textbook, but it will be given to you at any rate in any of these questions that you're trying to solve. And we're going to rearrange the equation to solve for C0. So the first thing that I'm doing is I'm getting rid of that denominator. I'm bringing it over to the other side. I am distributing that 6.5 times 10 to the negative 5 to both of them. So make sure you don't skip that step. The next thing that I'm doing is I'm collecting all my like terms. So I'm going to move my constant values over to the right-hand side. And the last thing I'm going to do is divide both sides by 6.5 times 10 to the negative 5 to get C0 by itself. So when I do all of that, I get an initial value of that benzoic acid is equal to 4.4 times 10 to the negative 3. And in this question, I also should have put a capital M to show that it's a molarity. Okay, here is another question, another different type of question. And in this particular one, we're calculating Ka given an initial concentration of an acid and given the pH. So in this type of question, we're trying to solve for Ka. It won't be given in a chart, or it will be told that it's at a different temperature than 25 degrees Celsius. So it says a 0.1 molar solution of acetylsalicylic acid is found to have a pH of 2.27. And remember here, that's the first thing that I'm looking at here, is anytime I'm given a pH, really what I'm being given is a concentration of hydronium. I can easily calculate between the two, switch between the two. So I'm asked to calculate the Ka for this acid. So I'm going to take this question and I'm going to write out my equation. I've got acetylsalicylic acid plus water on the left-hand side. I've got hydronium and the conjugate base of that acid on the right-hand side. And I'm going to fill in the table with everything I know. I know the initial concentration. I know the initial concentrations of the hydronium and the conjugate base. And I also know the equilibrium concentration of the acid because I'm told that pH value. So I'm taking base 10 to the negative 2.27 to get that equilibrium concentration of hydronium. I'm going to continue filling in the chart, kind of my Sudoku puzzle, I know that both the right-hand sides are going up, left-hand side is going down, and I can calculate my equilibrium values because I have enough information in that chart. Now I'm going to go to the Ka expression where my products are over the reactants, and I'm going to fill in everything we know. This is one of the simpler type questions, actually. So once I plug in all my results there, enter it into the calculator, I get a Ka value of 3.0 times 10 to the negative 4. And you can see with my sig figs calculating, the initial molarity of that acetylsalicylic acid, I had 3 sig figs. However, with the pH, because I'm reading after the decimal point, I only have 2 sig figs, so my final answer can only have 2 sig figs as well. So that concludes the lesson for the first part of 4.5. And in the next lesson, we're going to be looking at the KBs, very, very similar problems, with one little added on thing on top of that. So I hope that helps, and good luck with the practice problems.